Today I'm going to review an online convex optimization paper with the title of Adapting Algorithm for Online Convex Optimization with a Long-Term Constraint, which was present in ICML 2016. In general, an online convex optimization called the OCR problem can be formulated as a sequential and repeated game between the learner and the adversary. In each round T, the learner first plays the vector xt as an element of the set X, where the set X is a compact convex set corresponding to a set of possible solutions. The learner then incurs a loss ft over xt for playing vector xt, where the function ft xt is defined by an adversary. As all we know, we say that a function ft is a strong convex with a modulus sigma. This is the convexity, and adding to this sigma term, we can say that there's strong convexity. An online convex optimization problem. The learner objective is to generate the sequence of vector xt as an element of the set X over T that minimize the cumulative regret over T rounds lead to the optimal vector X star, where the X star was set in advance as an best vector. Several algorithms try to achieve sublinear cumulative regret in these settings. In the seminal work on online algorithm based on projective gradient descent, achieved a cumulative regret of order t to the 1 of 2 when the set X is the convex and the loss functions are also Lipschitz continuous over set X. In other words, online gradient descent achieve logarithm regret bounds order log t on appropriate choice of step size and on the strongly convex loss function. In the previous work, the constraint on the vector xt is assumed to hold in round t, such that a projection step is applied every round to enforce the feasibility of each xt. For general convex set X, the projection step may require solving auxiliary optimization problem, so it can be computationally expensive since the complexity of the convex set is high. More importantly, in practical application, the learner may in fact only be concerned with satisfying long-term constraint, that is, cumulative constraint violation should not exceed a certain amount by the final round t. In this work, we consider online convex optimization problem where the learner is required to satisfy long-term constraint which enable us to avoid computationally potentially expensive projection onto the domain, the set X of X, in each round. Let's see the problem statement in this paper. Let the set of xt be the sequence of vector played by the learner and ft the corresponding sequence of the incurred loss. The considering ft of xt a sequence of the convex function, we aim at minimizing cumulative regret subject to the following long-term constraint, where J is a M convex function which induce a convex constraint set. They also assume that the set X is bounded so that it is included some Euclidean ball B with a radius positive R. As is typically assumed in online learning, the function ft and j shall be taken Lipschitz continuous, and we further assume that the subgradient ft and gj are bounded by some finite g. Finally, they assume that there exists a finite such that the constraint functions are bounded over D. Following previous work, we consider a saddle point formulation of the optimization problem. The function is defined by the loss function ftx and the maximum value of jth gx with a sequence of a positive number theta t, and the lower of gt is the aggregator, the m constraint into a single function. In the saddle point formulation 2, we alternate between minimizing with respect to the prime value x and maximizing with respect to a dual parameter lambda. A closer look at the function lambda indicate we penalize violation of the constraint gx with a regularization parameter theta t. In the sequel, we use primal dual descent to minimize the primal value x, and we use dual ascent step to maximize the dual parameter lambda, where pi c stands for Euclidean projection onto the convex set C, while the set eta t and the set of mu t are sequence of non-negative step size that would respectively drive the update of x and the lambda. The step sizes, which are different for update of x and the lambda, are listed in Table 1. The parameters are divided into two cases, one convex, another strongly convex. We provide the result from the analysis, the next slide. We begin by listing three sufficient conditions for obtaining sublinear regular bounds for proposed algorithms. C1 and C3 impose the constraint on the decreasing speed of the time step size, while C2 couples the behavior of the three sequences to guarantee their validity. C1, C2, C3 are expressed if t is greater equal to 2 because of our choice for the initial condition lambda 1 and the lambda 1 and x1 are set to 0. Our main result is described in the following theorem. The theorem 1 can be further simplified in the convex case, forgetting momentarily about the dependency on the set of dr gf. It can be stated as follows in the case of sigma 0, and this is the cumulative graph found in the strong convex case, such as the sigma more than 0, and the bounds have the same leading term but are tighter. And condition 2 couples the loss and constraint regret, suggests that logarithmic regret for the loss would result in non-balancing regret for the constraint. This non-trivial property is related to how fast the theta t is allowed to decrease. Intuitively, this is a tension between making progress in x with a large eta t and adaptively controlling the constraint violation via 1 over theta t. We first introduce a series of lemmas to prove theorem 1. We begin by upper bound the variation of Lt of xt and lambda minus Lt of xt lambda t with respect to its two argument. The variation is deduced by the saddle point formulation like this. By strong convexity of Lt with respect to lambda, we get this formulation. Finally, rearranging again with respect to lambda, substitute the inequality of the lambda minus lambda t plus 1 over square, result in the upper bound of difference of Lt with respect to lambda. We now turn to lower bounds of variation of loss t. Based on the saddle point formulation, we simply notice that if gx star is less than equal to 0, we get obtain lower bound by summing both sides over rounds like this. And lemma 3 is dealing with the upper bounds with respect to both differential summation of xt and lambda t. To prove lemma 3, we shift to index in sums for terms that depends on at plus 1 over eta t, and collect term that depends on at, and we then use a minus 1 equal to norm over x, which is equal to r square. We again shift index in the sums of terms that depends on bt plus 1 over mu t, and collect terms that depends on bt, and we then use b minus 1 equal to lambda minus lambda 1, which is equal to lambda square. To conclude, now we present a key lemma of analysis in this paper. Lemma 4 is a cumulative regret found of under the three sufficient conditions C1, C2, C3. To prove this lemma 4, we start from formulation of Lt over xt lambda minus Lt over x star lambda t, which is equal to this formulation by adding Lt over xt lambda t and subtracting again. So this formulation consisting of lemma 1 and lemma 2. Lemma 1's upper bounds again, we return by upper bounds of lemma 3, and by the triangle inequality of subgradient of Lt with respect to lambda and x, so we can get these upper bounds, and this is the lemma 2's lower bounds. So combining these two upper bounds and the lower bounds, we get the upper bounds like this, where the RF is upper bounds of sum of delta ft. Finally, when maximizing the left-hand side with respect to lambda, we get this formulation, which enable us to deduce the upper bounds of gxt like this. With the above lemmas, we now prove theorem 1. For the proposed choice of theta t and mu t and eta t, we can verify that C1, C2, and C3 holds. By choice of eta and theta in table 1, we can get a convex case of a summation of mu t and eta t and theta t. The terms u can be obtained by summing the series of 1 over eta t minus 1 over eta t minus 1, which directly simplify by telescoping for the sigma equal to 0 case. As a result, we can obtain lemma 4 for both the cost and constraint. We obtain the desired conclusion by noticing that for any t greater equal to 1 and beta in either 0 or 1, and we have t to the 1 minus beta of 1 minus beta, upper bounds 1. Next, we showed our result to apply in specific case where additional assumption on gradient of g can translate into an absence of constraint violation. So we assume there exists a positive gamma value and a positive R value such that the variation of g are low bounded as L2 norm of gradient of gx is greater than R value. Let's denote x gamma is equal to the set of x in d-dimensional vector where gx plus gamma is less equal to 0, and this x gamma is subset of the set of x. The gap between the optimal value of the original optimization problem and that of problem of x gamma can be well controlled as a function of gamma, where the x star and gamma, x gamma are solutions respectively. With this assumption, we get upper bound of summation of delta ft without constraint violation. To prove this, we do same analysis with replacing g gamma x equal to gx plus gamma and t equal t plus gamma. As per summation of gx over t, which in turn leads to the same direct bounds as the previous state minus and contribution minus gamma t, and we cancel out the constraint violation scaling in order t to 1 minus beta of 2 by choosing gamma equals c1 t to minus beta of 2. The regret bound is minimized for beta 2 of 3, leading to a regret of order t t to 1, 2 of 3 with no constraints violation. They prepared two set of experiments to validate the regret bounds obtained for our adaptive algorithm with a long-term constraint and compare the algorithm on two benchmark datasets. Doubly stochastic metrics appear in many machine learning and optimization problems, such as clustering applications or learning permutation, and they consider sequence of random permutation matrix YT in L in p-dimensional real vector. Since permutation matrices are known to constitute the extreme point of the set of DS matrix, they try to find the closest DS matrix X by solving this optimization problem online, subject to the doubly stochastic linear constraint, and they have D and FTX and M to describe all the linear constraints. More specifically, there are power p-square non-negative constraint along with inequality to model the 2p equality constraint. These lead to following instantiations of the parameter controlling ft and gt and g and d. The cumulative regret for loss and the long-term constraint are shown in Figure 1 and Figure 2. They are compared over t equal 1000 iterations with d equal 64 and are averaged over 10 random sequence y. The results shown in Figure 1 and Figure 2 indicate that although the cumulative regret bounds for strong convex AOGD are not demonstrated to be tighter in our analysis than those of a convex AOGD, they achieve better cumulative regret for this problem, especially with respect to long-term constraint. And also, while convex mirror flux and convex AOGD should theoretically exhibit the same behavior, the result suggests that the mirror flux is not able to decrease cumulative regret at the same rate as our proposed method. Next, we examine the application of sparse online binary classification. Our goal is to minimize the long loss subject to constraint elastic net penalty like this, and where the YT and UT denotes the sequence of the label and the feature vector pair, and rho is the parameter that measures the degree of the sparsity of the solution of 7 equations. Our setting like this, ft is set log over 1 plus exponential of minus ytx transpose ut with a hyperparameter m, gx, and r and g and d. Like the results are reported in Figure 3 and Figure 4. Represent an average of 10 random sequence y and u. As a result, starting from x1 equals 0, we found that the iteration generated by convex OGD do not approach the boundary of the domain, hence increasing regret on the cumulative loss. Although our analysis predicts the cumulative regret of a convex OGD associated with the loss should be smaller than the associated with to the convex AOGD, These convex AOGD achieve a lower cumulative regret. This observation may be explained by the same argument as the one invoked previously, namely the larger step size at initial time step of convex AOGD enable us to make faster progress. We conclude by discussing several generalizations. First, in diagonal matrix of step size, each coordinate x is updated adaptively, which was proven useful in practice and several experiments. Second, with a strong convexity of loss and constraint function, we achieve logarithmic regret under different and strong assumptions. Third, with a Euclidean ball for B, we could consider set enclosing X more tightly while preserving the appealing computational property in experiment. Finally, we had a better finding a feasible penalty term to minimize the regret bound further. As a future work, this is the end of my presentation. Thank you for listening.